So today we're going to be talking about a brief introduction to information security. My name is Tyler Moore from the University of Tulsa. So, goals for today. We're first going to go through some definitions, what we mean by security, what we mean by digital information, and what we mean by information security. Then we'll go into what computer systems and networks are, relevant discussions related to security. We'll talk about the architectural decisions that matter, and so does some of the important network architectures. So, to the definitions. So, if we think about security, it's nice to contrast how we approach security versus how we approach safety. There's a very long tradition in the safety community to try to deal with accidents. Whereas in security, rather than protecting against accidents, we're protecting against intentional malice. In the safety community, you think about threats against nature. So you sort of random events that can occur at any time, and their targets are also randomly selected. Whereas in security, we defend against intelligent beings. Safety can be modeled using probability theory with historical data because we're dealing with these random events that tend to follow probability distributions. Whereas in security, we can't always make that expectation of randomness because adversaries are strategic in how they select targets, and they react to the defenses that the good guys put up. We're literally in a sort of cat and mouse type game. And for us, this is important because we're talking about economics, and economics is the strategic interaction of agents, and so it's naturally suited to studying security. Another way of looking at this is to think about a safety threat is a tornado, whereas a security threat is a terrorist attack. So this building here is the Alfred Murrah building in Oklahoma City that was targeted by Timothy McVeigh more than 20 years ago. So a question for discussion in class is, well, if you were in charge of the building security, how would your preparations differ when you're thinking about how to protect inhabitants against a tornado versus a terrorist attack? So when preparing for a tornado, should you consider whether neighboring buildings have been protected? So let's talk about information. So digital information is information encoded in discrete numbers, so just literally taking a symbol or any idea and then mapping it onto a numerical representation. And that's kind of one of the big ideas of computing is going from ideas to this numerical representation because then it becomes easy to store and manipulate things using computers. So on this slide here, we have an ASCII table. So what this is an early example of how we map letters and other symbols onto a numerical representation, and this shows both the decimal and hexadecimal representation. So we can translate the word hi exclamation point into its hex representation by looking at the table. So what are some of the implications of representing information in this digital way? Well, first of all, it's costless to create perfect copies. Whereas if you go back throughout history, before the advent of computers, making copies of anything could be very laborious. You think, it could be a matter of having to go in and write the same information over and over again. But digital information changes all that because you have this perfect representation, and it's easy to create a copy of it that costs virtually nothing. This has significant implications for how the economics of information works. Additionally, information can be transmitted anywhere immediately. So this makes it very easy to have collaborations with people across the world, and also makes it easy for attackers to come in and steal your data, even if they're living in a different country on the other side of the globe. So information can also be remembered indefinitely. So this is positive, and that allows you to keep a detailed record of transactions. We're in this era of big data where companies are just storing data in hopes of finding a use for it later. But this could also have security implications because what if a bad guy gets a hold of that data? Lastly, digital encoded information lacks provenance. The way that we choose to represent information means that we can't necessarily tell where that data has come from. We don't have an audit trail of all the different uses and accesses and manipulations of that data. So that means that modifications can be made in a way that aren't easy to identify just by looking at the data. So sort of one way of thinking about this is there's this thread of Photoshop, right? So someone can edit a picture, and you can't tell what's real and what's fake. Well, that comes fundamentally down to the lacking of provenance in our information that we represent this way. Okay, so we talked about security. We talked about information. What's information security? Well, at its most fundamental level, information security is an endeavor that tries to achieve protection goals specific to information. And it sort of boils down to three high-level goals. One is to protect confidentiality. And by confidentiality, we mean that information is accessible only to authorized parties. Another common protection goal is integrity, to try to protect the integrity of information. And what that would mean is that any modification of information can be detected as such. So it's not quite the same as saying that you can prevent such modification, but it's sort of a more limited goal to say that you can, if someone were to make a manipulation of that information, you can at least detect that it's occurred. And then we have availability. And so what we mean by availability is that authorized parties can access information and use the resources when and wherever it's needed. Okay, so let's illustrate each of these goals. So let's say you have a stockbroker who's trying to initiate a purchase of shares on an exchange. And so he might want to create a message and say, I'm going to buy 200 shares of Google for whatever the current price is, and say $600.25. So that's fine, but what the broker might like to have is some confidentiality about that requested transaction. So he wants to protect against an attacker such as Eve, who could drop in and observe the communication and the request that goes by. So a few caveats about confidentiality. First of all, it doesn't cover prior knowledge. So what this means is that if you're trying to achieve confidentiality of information, you can only do it within the context of when that information is under your control. So prior to that information being under the control of an actor, we can't say anything about whether or not they actually achieve confidentiality. Another thing to note is that breaches of confidentiality, once they occur, they cannot be undone. So sort of stepping into the rabbit hole. There's no reversing that occurrence. And so, bear this in mind whenever you hear in the news about all the latest company or government agency who lost 100 million records of their customers' information. And so once that confidentiality has been breached, it's out there, there's no getting it back. This is also coupled with an observation that it can be very difficult to detect that a breach of confidentiality has even occurred, right? So you think about it, if someone were to say, break into your house, usually there would be a natural trail, a broken window, or something, or that some of your stuff is missing. Well, in the case of a breach of information, someone has just accessed the data. You may not even see any trail at all. So this makes detecting that a breach has occurred very hard. So a question, again, for discussion in class is, what characteristics of digital information make protecting confidentiality difficult? Okay, so we've talked about the confidentiality. What else might you like to protect? Well, you'd like to protect the integrity of communications. So the broker, in addition to wanting to make sure nobody can observe the request to, say, buy 200 shares of Google, he definitely doesn't want an attacker who can come in and manipulate the order and say, we have Mallory come in and buy the shares instead of paying $600.25, maybe only paying $550.25. So that is obviously a concern. So a couple of caveats here. Again, protecting integrity is not the same thing as correcting modification. You just have to detect that the modification has occurred. And most integrity mechanisms take steps to ensure that the information has not been altered, so you can provide a guarantee of a lack of alteration. And integrity makes no claim of correctness, right? So it's perfectly feasible to have a data that has not been manipulated that is actually bogus from the start. So integrity makes no claim about the actual correctness of the underlying information. So, same question as before. What characteristics of digital information make protecting integrity hard to achieve? Availability. Again, back to our good friend the broker. He's buying the shares of Google, sends the message to the exchange. Well, an availability goal is that you want to make sure that the message actually gets to its intended recipient. So you could again have an attacker, Mallory, who might block the purchase and say block the message from being received to the exchange, and then issue their own request to buy instead. So availability is seen to be a lot harder to guarantee than confidentiality or integrity. So it turns out that using cryptography, you can often guarantee confidentiality and integrity quite formally, whereas with availability, it's much more amorphous. And why is that? Well, one is that the guarantees have to be made for not just the information that you're protecting. It has to involve the different principals who are involved in the information. So thinking back to the example previously, you're having to actually ensure that the exchange can receive the message. And you have to ensure that the broker can actually transmit it. So you have to consider a broader set of actors. All right. So, and when we talked about availability, we said that authorized users need to be able to take and have access to the information. Well, who are these authorized parties we speak of? Well, who are they? How are they authorized? Who is authorizing them? So a couple definitions. One is when we refer to parties, we mean that they're like actual people controlling a computer system. So, but we can also think of them as programs that are acting on their behalf. And then the authorization is simply a decision that a principal must take on whether a party is allowed to undertake a task. Okay, and it turns out that this authorization decision is key. It's the fundamental challenge of security engineering, deciding which parties should be allowed to access, manipulate, or read information. Okay, so we've talked about the protection goals, confidentiality, integrity, and availability. Now I want to talk about a related issue, which is identification, authentication, and authorization. So these may all sound like the same thing to you. In fact, if you look up in thesaurus, these might even be synonyms. But in fact, they're actually quite different in subtle ways. So identification, authentication, and authorization answer different questions. Identification answers the question, who are you? Whereas authentication says, is it really you? And authorization says, okay, knowing who you are and who you are, who you say you are, do you have permission to do something? Are you allowed to do this? It's very common to see people conflating these concepts. And what you'll often see is that people will suggest a technical solution that may provide authentication. Say a biometric that reads your iris or takes your fingerprint. And people will often say, all right, well, we've got this authentication solution that's going to solve all of our problems, when their problems are in fact authorization problems, deciding who is actually entitled to access a system. Coming up with a fancy authentication mechanism isn't going to solve that problem. It just solves the problem of saying, is it really you? Are you the identity that you claim to be? So let's dig in a little deeper here. So let's talk about how computers identify people. So in order to authorize a user to access computer resources, systems have to figure out who they're interacting with. And computer systems store these ID attribute pairs, typically in a database, where the claimed identity has an attribute associated with it. Upon encountering a user, the system will ask the user for their ID and this attribute. This identifier should be unique, and the attribute can be used to authenticate the identifier. So that only works provided that the attribute is known only to the user and nobody else. If that's the case, then it can be used to authenticate the user to the system. So if you have, say, a password that's associated with an identifier, if that's kept secret, and the only person who knows it is the user, the person or user who's associated with that identifier, then the password can authenticate the user. So let's talk about a case study here. So we have a person who wants to go to an ATM to take some money out of their bank account. So there's an identification, authentication, and authorization steps at each point. So first we have the identification step where the customer inserts their card, which is a card number, which identifies the user and account to the ATM. The ATM, looking at that identifier, says, okay, tell me your PIN. So there's a request to authenticate that user. The user enters the PIN, and then the ATM then authorizes them request back to the bank, and then if that passes muster, then the authorization can take place. So the ATM establishes that the identifier provided has been authenticated. So then the decision becomes, okay, how much should we withdraw? We're going to request $100, and then the ATM communicates back to the bank and says, okay, is my balance greater than $100? Do we actually have the money in the bank? The bank says yes, it's approved, and then you are then authorized to receive the money. And then you get your cold hard cash. So you can see we have three distinct steps here. We have identification by providing the card. We have authentication by providing your PIN, which is a secret that can authenticate the user that's associated with that ID. And then authorization decides whether or not you're entitled to take the step based upon your proven identity. So where do things go wrong? Well, they can go wrong in a few ways. One is for an ATM that will fail to authenticate a user correctly. So how could that happen? One case, it would be that Mallory comes along and guesses the PIN, perhaps because the user selects their PIN as 1234, and Mallory gets a copy of the card. She can claim that identifier and then enter that PIN and gain authorization. But that's not the only way. And a more subtle way that's often used by criminals is for the ATM to incorrectly authenticate the user. So this is a card skimming device, and what that does is sort of gets placed on top of an ATM and placed there by a criminal who then reads the identifier that's provided on the card as it goes through the mag stripe. The user interacts with the ATM, thinks all is well. But then what happens is, in this case, in addition to sort of skimming the identifier, the attacker will typically have like a pinhole camera placed at the ATM so they can observe the PIN that has been entered by the user. And once they've observed that, they can then create their own cloned copy of the card and then go to another ATM and provide the PIN to get as much money as they like. So what we have here is an authentication failure where the user doesn't authenticate the ATM. So this is another way to go about it is for the user to fail to authenticate the ATM. So with the card skimmer, the ATM's not authenticating the user correctly, but it can go the other way, where Mallory could just set up a fake ATM and the user comes along and thinks this is really an ATM owned by the bank. And then they provide their information, and Mallory can then glean the card information in the PIN. And so there have been a few instances of this where a malicious ATM has been set up. This one was set up at DEF CON, a big hacker conference, a few years back. So, but authentication failures become even more problematic when we think about the online space. And so when we think about phishing attacks, we want to know, how does authentication fail on phishing? So I want to discuss this whenever we meet in class. So think about what are the identification, authentication, and authorization steps here, and who's identifying and authenticating whom, and how can an attacker succeed? Okay, so that wraps up our discussion of information security and information security for today. And next we'll talk about computer systems and networks and sort of key concepts relevant to security. So there are 4 fundamental ideas of computer architecture that we'll briefly discuss here that I think are especially relevant to security. First up is code as data. So this is sort of almost like a koan here, where you could sort of think of this as like a philosophy. Is the code data? Is the data code? This means something quite specific, and when we think about how our modern computer architectures work. So the most pervasive computer architecture in existence today is the von Neumann computer architecture. So John von Neumann was a sort of prolific mathematician, computer scientist, one of the founders of game theory. So he was quite prolific, but he designed an early computer architecture that is still being used today. And the key aspect of that architecture relevant for us is that it does not distinguish between instructions for computer programs and data. So basically everything that gets stored in memory is both data and code. It's all sort of put together in the same common memory space and not distinguished between them. And so that's what we mean when we say code is data. And this is a quite powerful concept because it enables great flexibility in reprogramming computers. By setting up this architecture in this way, it was possible to have sort of some memory that could have data in one instance and then be overwritten to have code in it. And then so it enabled reprogrammable general purpose computing. It also helps contribute to the fact that programs can be costlessly copied and reproduced because they're just being translated into their digital representation. So it's not only data that can be costlessly copied, so can programs. This is great, but it has a lot of unfortunate security implications. The biggest being what we'll call a buffer overflow attack. So this is code as data's dark side. So you can sort of look at this here, and we have this sort of visual representation of a memory map. So the bottom figure here shows what you have various bits of memory which have been allocated, and a certain fixed amount has been allocated for data as input to a program. And then after some period of time, there's another part that's the program, and that's the dark shaded color. And the machine knows that input data can't be executed, whereas code needs to be executed. And so what an attacker can do is he can provide an input that is bigger than the program intended. And so he can fill up the input buffer and overflow it, and so that he can get his malicious code into the executable spot so that it can then be executed. And these buffer overflow attacks sort of form the basis of a whole class of attacks, which you'll hear about more. The next thing we'll talk about after code as data is abstraction, and it's important. So what do we mean by abstraction? Well, abstraction specifies the meaning and behavior of software while hiding the details of implementation. So this is sort of a fundamental concept of computer science, and we encourage, and as you learn in your programming classes, that you should write modular code. And the importance of modular code is that it exploits abstraction, and so you can sort of define a method which would implement a certain function, and others can use that function without needing to know exactly how the implementation worked. And so this enables composition of functions and code reuse, which makes computer programs much more powerful. They in turn enable rapid software development. And what's sort of interesting from a software engineering perspective is that there's no limit to all the combinations of code that can be made, right? So you have as you have more and more libraries, they can be composed in more different ways, which enables rapid innovation. It also makes it very difficult to identify and prevent malicious combinations of code. There is sort of a stereotype among computer scientists that they feel like you present them with a problem, they say, oh, well, what we need to create a new framework, and you sort of abstract away the details of the problem, and that will lead to an elegant solution. Well, sort of one cynical take on this is that there's a view that all problems in computer science can be solved by another level of indirection. And it is to a certain extent true, and that many powerful solutions in computer science do rely on additional abstraction. And so one way in which we see this abstraction manifest itself is in the layered architecture of computers. So what we have different layers of abstraction, which can be implemented at each level, assuming the other layers are operating correctly. So we have the lowest level, we have hardware. Above that, we'll have the operating system. Then we have libraries, which are sort of predefined chunks of running code that others can leverage. We have applications which plug into those libraries, which interface back to the operating system, and then we have active content on top of the application layer. So the question is, are these layers a good or a bad thing? Well, they're on the plus side, they enable greater compatibility, since each layer only needs to really concern itself with the adjacent layers. And this means that developers can safely ignore problems that are already solved with other layers. So if you are writing a web browser, you don't need to think about how the hardware works on a machine and how that interfaces to the operating system. You can just assume that problem has been solved. So that's very powerful. But on the plus side, on the downside, is that these higher layers can't identify or prevent malfunctions at the lower layers. So if you have a security problem in a lower layer and a different layer, then it can actually percolate through the stack. And so you may have written great secure code that operates at one layer, but if there's a layer that it interacts with which is insecure, that could be a way for an attacker to get in and cause problems. So a flaw in a single layer can affect all the software that's developed on top. So if you think about it, how Windows used to be woefully insecure, so in the early 2000 period, late 1990s, it didn't matter how secure the code that was being written on the applications that ran on Windows, because an attacker could come up with an exploit that would allow them to take control of the entire operating system due to flaws in Windows. So these layers, from a security perspective, can actually be quite bad. So one way to think about this is to say, well, what layer can a strategic attacker wreak the most havoc at the least cost? So we'll make an amendment to Professor Wheeler's famous quote by saying, all problems in computer science can be solved by another layer of indirection, except security problems. In fact, those are magnified. Okay, another big concept, which you've probably heard of, is called Moore's Law. This is essentially an exponential growth in the computing power. So this was noticed by the founder of Intel, Gordon Moore, no relation, who noticed in the 1960s that integrated circuit density had been doubling since the 1950s, and it turns out that the density of your integrated circuits directly corresponded to the computational power. And he sort of said, all right, this doubling seems to be occurring, and he predicted this trend would continue, and this and this sort of became a self-fulfilling prophecy, and that became a target for companies like Intel to keep improving the overall performance and doubling the computer performance. And it seems to have held that computer performance has roughly doubled every 18 months, and this has continued, and everyone keeps talking about it dying, but about it no longer holding, but it seems to roughly still hold today. And just sort of for fun here, this was Gordon Moore's. This is a picture from Gordon Moore's original paper in 1965, which came up with how he envisioned computers might evolve and take advantage of this exponential growth. So this is sort of a picture of people at a department store, where they might go to different parts of the store, notions and cosmetics, and then handy home computers where people can come and get their own computer they could hold in their hand. It seemed like such a fanciful idea back in the day, just 50 years ago. Okay, so the next concept we'll talk about is the halting problem. So for those of you who have taken or will take some of the more formal methods courses in computer science or theory of computation, you will study this problem in great detail, but it's sort of interesting to note that as early as the 1930s, Alan Turing came along and proved that it's impossible to write a general purpose program that will determine whether another program will stop. So the idea is, wouldn't it be great if you could just have a program that would take some code as input and then tell you whether or not that code is going to stop? Because one of the problems we have with code is you can have something that will get stuck in an infinite loop or hang indefinitely. And it seems like it would be feasible to do, but in fact, he proved that in general this is not possible. And from this, we've even seen subsequent proofs showing that the identification of virus or malicious software by an antivirus program, that task reduces to the halting problem. So bear this in mind the next time someone complains that software developers should be making secure code and that antivirus companies should be able to detect all malicious code. Well, it turns out that it's a fundamentally hard problem that we're never going to have a solution to. So last thing we'll talk about is the internet. So this is a picture of the early internet in the 1971, whenever it first began. It's long been recognized that there could be value in connecting computers together, so research began by developing these protocols that specified how different independent computers could communicate with one another. These networking protocols take advantage of the same abstraction that we saw when considering computer architecture. So this is what the networking protocol stack looks like. You have the physical layer, data link, network, transport, and application layer, and various protocols that lay on top of it, some of which you may recognize. So the physical layer is something like 802.11n, which is an IEEE standard. We have the data link layer, which is Ethernet, network layer, which has different protocols, the two big ones being TCP and UDP. Transport layer is IP, and then various application layers on top. HTTP is for the World Wide Web. SMTP is for email. BGP is for the Border Gateway Protocol for different networks to route across the global internet. So, what is the IP protocol? Well, in IP version 4, we have every computer has a 32-bit unique address, such as the one I indicated here. So you have four numbers, each of up 0 to 256, which is 8 bits. So 8 bits times 4 is 32 bits. And so any computer should be reachable using its IP address. So on the entire internet, everyone has a public IP address, and you can find it. At the transport layer, you have TCP, which establishes a connection between devices for sending traffic, and UDP, by contrast, is connectionless. Their data just gets pushed over that transport layer, and if the connection doesn't go through, it doesn't care. It just keeps going. It just gets discarded. And then the application layer, we have lots of different ones. So HTTP is a port 80, it's protocol for websites connecting, to this 129.119.7.166. Port 80 delivers you to the SMU homepage, and SMTP is port 25. It's protocol for sending email. SSH is how you remotely log into computers, BGP, and so forth. So, we're not gonna get into the details of this. If you want to learn more, you need to take our networks class or our network security class. But I will just mention briefly one of the protocols here now to give you a sense of how security plays a role, because each of these protocols, when they were designed in the 1970s and 80s, didn't really consider security at the time, and so there's no built-in authentication nor confidentiality. As such, an attacker can cause real problems. So with BGP, you have something like this. You have these different autonomous systems which have numbers. Here we have AS1 through 4, and there are these routing tables that each border router at each autonomous system says, which tells you how to reach a range of other IP addresses and the cost of the path to get there. Well, it turns out that somebody who wants to manipulate this can come in and do so by just announcing a route that is shorter than the other one, and that will then allow people to just believe it, because there is no there's no mechanism for ensuring trust in these networks. It's just if someone announces a route, it must be true, therefore we're going to believe it. And so there have been a number of attacks where these false announcements have been made, which redirects traffic and causes internet outages. For more information, you can read this report here that some researchers came up with, which looked at the overall resilience and security of the global routing infrastructure. What they found is that even though there are a lot of security problems here, and that it is possible to carry out these attacks, in practice the system works reasonably well, because of the human layer of managing the system and reacting to outages. So in general, internet protocols incorporate a number of design decisions that have a negative impact on security. One is that IP makes computers globally addressable. Anyone can be reached because you have this public address. Packets are delivered on a best effort basis. Meaning there's no guarantees, and so if you don't receive a packet, you can't be sure if it was just bad luck or a malicious blocking of the packet. There's no built-in authentication protocols, which makes spoofing possible, and this design itself is inherently decentralized, that you have these autonomous networks, which makes who have their own management structure and their own control, and so any attempt to try to coordinate overall responses within the internet is very difficult, and often fails. And so that while there have been many proposals for more secure or secure versions of many of the protocols I just talked about, it can be very hard to coordinate upgrading to the more secure versions because of this decentralized nature. So that will cover what we are going to talk about today. Or as a reminder, we defined what security, information, and information security are. We gave a sort of a quick rundown through some of the characteristics of computer systems and networks which are important for understanding security. And I thank you for your attention.